Hi, welcome back. Today we will be solving Physics Higher Level Paper 1, November 2016, time zone 0. So it's going to be a 1 hour paper and no calculators are allowed. Alright, let's get started. Question number 1. A boy jumps from a wall, so the boy must have some mass. So no. From a wall 3-meter high. So let the height be 3 meters. What is an estimate? So it's an estimation problem, so we have to probably estimate the mass of the boy because no weight given to us. Of a change in momentum. So change in momentum. So this triangle represents change, small change. Of the boy when he lands without rebounding. So this is a situation here. So there's a boy here. It has some mass, which is unknown. We probably have to estimate it. This is the ground. Height between the ground and the ball is something. 3 meters. Okay. Now the boy jumps from initial velocity of 0 because there's no initial velocity here. It was at rest. And then at the moment where it lands, it has some final velocity. From the data booklet, we know that momentum is mass times velocity. So change in momentum is due to mass times change in velocity because the mass stays constant. So any change in velocity will lead to change in momentum. Let's further expand it. Change in velocity is final velocity minus initial velocity. So it's the difference between the initial and final velocity. Whereas we already know from our diagram here, your initial velocity is 0 because the body starts from rest. So this is going to give us change in momentum equals to mass times final velocity. So this is the equation that we will be using. Okay, now the whole problem is to find the final velocity achieved after falling at a height of 3 meters. So we know the body is falling. So when the body falls under the influence of gravity, it releases potential energy. So by applying conservation of energy, we can see that the entire potential energy released during the fall is converted into kinetic energy at the bottom of the bottom. Yeah. So the entire potential energy released during the descending height is converted into gain in kinetic energy. So we gain the potential energy lost during the descent is equals to gain in kinetic energy. So kinetic energy is gain. So lost and gain. Right? So using conservation of energy. So potential energy from the data book is given by mgh, and kinetic energy is given by half mv squared. These two masses can cancel out each other, and then we can make v the subject. So if you move this 2 to the other side, it becomes 2gh equals to v squared. Now get rid of this square, but you can square root on both sides. So v equals to square root of 2gh. Sub this v into this v, we will get this v can be replaced by this v, which is equals to square root of 2gh. Now we have to approximate some values here. Mass. So my mass will be around 60 kg, 60-65 kg. 60 is not a nice number to deal with, especially doing manual calculations. So I will suggest just use a 50. 50 may be easy to calculate by hand. Do mathematical calculations. So 2 times g. G is 9.81 exactly, but for the purpose of estimation, we will round up to 10. It's easy to calculate. And height is given to us as 3. This is going to be 50 square root of 10 times 3 is 30, into 60. How to find square root of 60? Now, let's see. 7 squared will give us 49. And 8 squared will give us 64. There we have it. 64 is our closest number to 60. So if the square root of 64 is 8, then the square root of 60 will be a number very close to 8. Slightly less than 8, maybe 7.8 something like that. So we can approximate this thing as 8. So 50 times 8 is around 400. Approximate. 400 is our answer. There's no option that says 400, but is there any option that is closest to 400? Yeah, it is 500. So 500 is closest to 400, that's why we will choose part C. Question number 2. A car moves to north, so we can north, east, west is involved. So we have N, E, W, S. At a constant speed, so there's a car here. This car moves north at a constant speed of 3 meters per second for 20 seconds. And then east, and then it moves east at a speed of 4 meters per second for 20 seconds. When it reaches there. What is the average speed? Now the formula for the average speed equals to total distance over total time. That's the formula. Average speed equals the total distance over total time. So we need to find the total distance. Oh, but we already have the total time. So the total time of the journey is 20 due north and 20 due east, which is 20 plus 20 is 40 seconds. And the total distance we need to find out. So speed equals to distance over time. This is the formula that we will be using. Distance will be equals to velocity multiplied by time. This is the equation. So we have two cases there. So the first case we will use 30 meters per second during 20 seconds. So speed will be 3 times 20. For the second case, which is traveling due east, it will be speed, which is 4, and the time is also 20. So 4 times 20. So this will give us 80 meters, and this will give us 60 meters. So we have to add them together. So this is 60 meters, and this distance is 80 meters. So if you add them together, 80 plus 60, so 80 plus 60 is 140. Now we have to simplify these things. So 0, 0 cancels out, 2, 2s are 4, 2, 7s are 40, so we have 7 divided by 2, which is around 3.5 meters per second. So there we have it. C part is the answer. Total distance, total time, find the total distance and divide by the total time. Alright. The student draws a graph to show the variation with time t of the acceleration of a of an object. Now, before solving this question, remember this thing that if I give you a graph of displacement versus time, velocity versus time, and acceleration versus time, in order to go from displacement versus time graph to velocity versus time graph and then forward, you have to find the slope of the graph, gradient of the graph, or derivative of the graph. So in physics, we don't perform differentiation, we just find the slope of the graph. Now, in order to go in the reverse direction, so if I give you a graph of acceleration versus time, you need to find velocity, you just need to find area under the graph. Okay? Okay, area under the graph. Displacement, velocity, acceleration. This is how you're going to change between these three graphs. So right now we have a graph of acceleration versus time. What can we deduce? What can the student deduce from this graph only? And what quantity from the graph is used to make the deduction? Okay. So we have acceleration versus time graph, and we have quantity used. So quantity is either gradient or the area. Okay. Let's talk about the slope, the gradient. Okay. So the gradient of the graph. So this is a graph of acceleration versus time. So if you were supposed to find its gradient, finding its gradient means moving even forward, which means there's nothing here. So we don't know what does the gradient of the acceleration gives us. So whatever it gives us is just meaningless here. So the gradient of the graph of this graph actually doesn't give us anything. So gradient of the graph, just ignore the option that says gradient of this graph. But the area, if you have a graph of acceleration versus time, the area of this graph does give us a meaningful quantity, which is change in velocity, right? Any change in acceleration will give us change in velocity. So any option that says area under the graph and velocity is the answer. Question number 4. A mass is suspended from a ceiling of a train carriage by a string. The string makes an angle of theta with the vertical when the train is accelerating along a straight horizontal track. So it looks like acceleration is a vector quantity, so it is direction dependent. So now we have a forward acceleration, which is A. Okay. Now if you look at this triangle very carefully, if you look at this ball. This ball is undergoing a horizontal acceleration. Okay. So it has an acceleration. So what is the acceleration of the train? So we need to find the acceleration of the train. When the train is accelerating along the straight line. Okay, what is the acceleration of the train? Alright, let's do it. If you look at this triangle carefully, what we need to do first of all is to resolve this triangle into two components. So imagine this is a ball here. Now this ball will have two components of acceleration. Acceleration is a vector quantity, right? So it will have a vertical component and it will also have a horizontal component, right? It will also have this horizontal component. So this horizontal component can actually be moved down here. The reason is so that we can draw this triangle. Okay? Right. If you're getting confused by this, let me draw again, maybe here. So this is a body. This body has two components of acceleration. It has a downward acceleration and it has a horizontal acceleration. And because of these two acceleration, it will give us some resultant acceleration here, right? So this is you can say horizontal, and this is vertical, and this one is net acceleration. Let's draw this triangle here again. So there's a body here. It has a downward acceleration and it has a horizontal acceleration. So I will draw horizontal acceleration instead here so that we can create a nice triangle, right angle triangle. Okay? And if you extend the diagram, it looks like it's supposed to be something like this, and there's an angle here. So if this angle is theta, then you can see this angle is also theta, right? Just by comparison. This angle is theta, this angle is also theta. And the downward acceleration is always due to gravity, so it's going to be g. And the horizontal acceleration is a. So a is the horizontal acceleration of the ball, which is same as the acceleration of the train. So in other words, when he says when the train is accelerating, find the acceleration of the train, in other words, he's asking us to find the horizontal component of the acceleration. Yeah, because the train is moving in the horizontal direction, and that is what we need to find, the horizontal component of the acceleration from this triangle. And the downward component of the acceleration is gravity. Right? Gravity is acceleration, gravitational acceleration, 9.81 meters per second squared. So if you look at this triangle, we can use a circle tool. So we have the hypotenuse, opposite, adjacent. Opposite adjacent is tan. So tan theta is opposite, which is A, over adjacent, which is G. So make A the subject, the horizontal component, this one. So A is going to be equal to G tan theta. So there we have it. Part C is the answer. Yeah. Okay. An object initially at rest is accelerated by a constant force. So let's look at this question first. So there's a constant force acting on it. So whenever you see the word force, always prepare yourself to use this formula. The net force acting on a body is equal to mass times acceleration. Acceleration and force are vector quantities, so they are direction dependent. Mass is scaling, no direction. Which graph shows the variation with the time t of the kinetic energy and the variation with the time t of the speed of the object? Okay. Now, looks like there's a constant force. So on the right hand side we have a graph of speed versus time. So as you still remember, displacement, velocity, acceleration. So going forward is finding the slope. So right now we have a graph of velocity versus time, and we need to find acceleration, so we have to find the slope of this graph. So the slope of all these graphs, slope represents acceleration. Acceleration. And this is acceleration. Well, if you provide a constant force, this constant force will provide you constant acceleration, right? Because the mass is also constant. So each three of the quantities here is constant. So it looks like this acceleration is constant. Constant acceleration will give us constant slope. So which of the graphs have a constant slope? So you can see this graph has increasing slope, so ignore this option. And this graph also has an increasing slope. You can see if we draw a tangent here, tangent slope, the steepness of the tangent is increasing, so ignore this one. So it will be either A or C, right? A or C, constant slope. This is a straight line. A straight line has a constant slope. Okay? Constant gradient, constant slope. Let's talk about the kinetic energy. What's going to happen to the kinetic energy? Well, kinetic energy is given by the formula half mv squared, right? Kinetic energy, so this is constant, half is constant, mass is constant. So kinetic energy is kind of proportional to square of v. So if you remember from your like mathematics, this is kind of a graph of y equals to x squared, right? Which is like a quadratic, a happy face, quadratic shape graph. The kinetic energy is proportional to square of velocity, so it's not going to be linear anymore. It's going to increase at a much faster rate, at a rate of square. So it's going to be like a quadratically increasing graph. That is why we will choose A part, because kinetic energy depends on square of velocity, which gives us a quadratically increasing graph. Okay, so it's going to be A part. Next question. Okay. Two stationary objects of mass 1 kg and 2 kg are connected by a thread and suspended from a spring. So we have a spring. So the spring is responsible to carry the weight of these two, and the thread is cut immediately after the cut. What are the magnitudes of the accelerations of the object in terms of the acceleration due to gravity g? So we have to give acceleration in terms of g, like how much g force, 1g, 2g, 3g, like that. So the weight is actually equals to mass times gravity. So if you look at this 1 kg, so on this 1 kg there is a g force of 1, mass is 1, and g, we will leave g as it is, it's going to be 1g. If you look at this 2 kg, the g force acting downward is 2g, right? Mass is 2 and g is as it is, so keep it as it is. So if you look at this spring, right now it is stationary, right? Stationary means there's no movement, so the net force must be 0. So if the net force is 0, it means this spring is responsible to carry the weight of everything that is below this dotted line, right? So the total weight or total g force acting below this dotted line is 2 plus 1. So 2g plus 1g, which is 3g. So there's a total of 3g of acceleration acting downward. Hence, the spring is also responsible to provide this much of g in the opposite direction to make sure that it carry the weight of these two. Right? That's why the whole system will be in the stationary. Now, at the moment when you cut the thread, if you cut the thread, let's just look at this 2 kg. This 2 kg will just fall under the influence of gravity. It will be a free fall. There will be no earth attached to this 2 kg. So when an object, independent of the mass, falls under the influence of free gravity, its acceleration of free fall will always be 9.8, which is g. So it doesn't matter how much big or small the mass is, as long as the body is falling under the influence of free gravity. So free fall, the acceleration of free fall will always be g. So let's see. Acceleration of 2 kg will be g. So it's either this or this. So ignore these two. Okay. Now let's just talk about what's going to happen with this 1 kg. This 1 kg is not falling under the influence of free gravity. There's no free fall for this 1 kg because it is attached to this spring. Now this spring is providing a force of 3g in the upward direction, whereas the weight of this 1 kg is 1g in the opposite direction. So we have to kind of subtract the two forces in order to find the resultant force. So 3g upward, 1g downward, so it will be 3 minus 1, which is 2g in the upward direction. Yeah, so 2g is going to be the resultant acceleration acting on this 1g. So this 3g upward, this 1g downward is no longer free fall because it's attached to the spring. Spring is providing some force. So 3 minus 1 is 2 in the upward direction. So it's going to be part D. Okay. Question number 7. An object of mass 2 kg is thrown vertically downward. So there's an object here, and it has some mass 2 kg, and you throw it vertically downward, right? So downward with an initial kinetic energy of 100 joules. So there is some kinetic energy here. Call it kinetic energy 1 initial, 100 joule. Okay. What is the distance fallen? So probably goes which is there, and this is the distance fallen by the object at the instant when the kinetic energy has doubled. So doubled. So this will be our final kinetic energy. Call it kinetic energy 2. So we are doubling the kinetic energy. So if you double the kinetic energy, it means if the initial was 100 joule, now it will be 200 joules. Double it, right? 100 plus 100 again. That means still falling down. And the question is, who's responsible to provide this 100 joules of kinetic energy, because of which the kinetic energy has doubled, right? Somebody has to provide this energy because energy is conserved. So we can see it's falling downward. When it's falling downward, when an object loses height and falls under the influence of gravity, there will always be loss of potential energy. So potential energy is always lost. So that loss in potential energy is responsible to provide this much additional kinetic energy. So we will say that potential energy lost equals to gain in kinetic energy. And we know that in order to go from initial kinetic energy to final kinetic energy, the body must gain a kinetic energy of 100 joule because it has doubled. But how much do you gain? You gain 100. 100 plus 100 gives you 200. And who's responsible to provide this 100 joules of kinetic energy? Loss in potential energy. And the formula for potential energy is just Ng and the height fallen. So the height fallen here is actually the distance that we are looking for. The distance traveled or the height fallen. So make height fallen the suffix. So height fallen is 100 divided by Mg. Replace variables with the number. 100 divided by mass is 2. And G is 9.81, but for the purpose of a simple manual calculation, we will choose just 10. This cancels out. 10 divided by 2 is 5 meter. 5 meter. Yeah. Okay. So number 8. A student obeys 615 climbs a vertical ladder of 6 meters tall in the time of 8 seconds. What is the power developed by the student against gravity? Power equals to energy over time. Now this energy can be any type of energy. It can be work done against friction, or simple work done, gain in kinetic energy, potential energy, electrical energy, any type of energy. But in our case, it is against gravity, so the work done against gravity will be potential energy. And then we have the time here. So potential energy's formula is NGH. Then the time comes in, so let's plug in everything. Now we're not given the mass of the boy, but we're given the weight. So the weight is equal to mg. we can do is we can replace this mg by just the weight, because weight is equal to mg. So simplifying from the equation, we get WH over T. So power equals to WH over T. Let's just plug in the variables and numbers here. Weight is 600 times height volume is 6, divided by time is 8. Okay. Alright. So let's simplify. And this is multiplication, or just put a dot here. A lot of the students are confused with multiplication with plus sign. Right? So 2 4s are 8, 2 3s are 6, 2 2s are 4, 2 300, 2 1, 2 150, and 150 times 3 is 0, 5, 1 getting 450. It's going to be 450 watt of power is developed while doing work against the gravity. Yeah, the SI unit for power is watt. Okay? This was the equation I used. Alright. Energy is supplied at a constant rate. Energy is supplied at a constant rate. It means that energy supplied at a constant rate means the power supplied is constant. Power is energy over time, so the rate of transfer of energy is constant, so power is constant. For a fixed mass of a material, the material begins as a solid, so probably there's a solid here, so there's a gas here, there's a liquid, so melting, and then after melting, vaporization, gas. The graph shows the variation of the temperature of the material with time. Okay. Specific heat capacities of the solid, liquid, and gaseous forms of the materials are specific capacity of the solid, and then the liquid, and then the gas, respectively. What can be deduced from the values of the specific heat capacity? So we need to figure out which one is the largest and which one is the smallest. Liquid or gas or solid in the correct order, ascending or descending. So we need specific heat capacity, so the formula given from the data booklet, so we know that Q equals to mc delta T. Delta T. So let me show you where this equation is. So it's given in the topic 3. This one. Q equals to mc delta T. Q is the thermal energy transferred, M is the mass, C is the specific capacity, and delta T is the change in temperature. So we are interested in finding C, so make C the subject. So C will be equals to Q over M delta capital T. So our capital T is a change in temperature, right? And our time is small t. So just be careful. Delta capital T means change in temperature, and delta T, or just say T or delta T is the time. Maybe we should call it delta T because the time never stays constant, it's always changes. Alright, let's see. So you can see the main difference between the solid, liquid, and gas on this graph is the slope. You see the slopes are different. This one is the most steepest, then this one is the least steepest. Let's figure out what does the slope of this graph actually represent. So call it S for slope. So slope is figured out by using rise over run. So on our rise, we have change in temperature, and on our run, we have change in time. And also this power is equals to energy. This time the energy is in the form of thermal energy, so it can be, it is Q, and time is just change in time. Make thermal energy the subject, so we have P times change in T. And next step is, let's just copy this equation here. C equals to Q over M delta T. The next step is replace this Q by this Q. So Q, thermal energy, is power multiplied by change in time. So we have P times change in time divided by M delta T. Now, you can see there's something that we can do about this term, this one. Something we can do about it. Slope is equals to delta capital T over delta small t. And here we have the other way around. So we can write it as a reciprocal of the slope. This is it. If this was in the correct order, like delta capital T over delta small t, then we will just replace this entire thing by S. But we have to flip it over because the order is a match. It's just upside down. So there we have kind of our final equation. So C equals to P over M over 1 over slope. Power is constant, mass is constant. So actually, the specific heat capacity is inversely proportional to the slope, or S, of the graph. So the higher the slope, the smaller the specific heat capacity. So we need to figure out which one has the highest specific heat capacity. So highest specific heat capacity means smallest slope. Let's see which one has the smallest slope. So you can see this is the most steepest. Then this comes in, and this one has the least. It is the least steepest because it's more flatter. So the gas. So let's write down the order. So this one is the most steepest, least steepest. So least steepest means highest specific heat capacity because they occur in inversely proportional. And after this one comes, this one is the least steepest, and this one is the most steepest. So the highest slope. So you can see here, the higher the slope, the smaller the specific heat capacity. So it's inversely proportional. So it's going to be gas, solid, then liquid. Gas, solid, then liquid. So it's going to be part. Okay. The pressure of a fixed mass of an ideal gas in a container is decreased at a constant rate, at a constant temperature. For the molecules of the gas, there will be a decrease in, well, pressure is decreasing, and the pressure of a gas is due to the collisions of the particles against the wall of the container. So if you drop the pressure, it means the frequency at which these gas particles are colliding against the wall of the container will also drop. So anything that tell us about number of striking particles against the container decreasing will be the answer. So we'll decrease in the number of striking the container walls every second. So less particles will be striking the wall in a given time. That's what pressure means. Colliding particles against the wall of the container leads to pressure. 10 Okay. And ideal gas of N molecules is maintained at a constant pressure P. The graph shows how the volume V of the gas varies with absolute temperature T. So this has to do with ideal gas. So let's just write down all the equations of an ideal gas. So the first equation for an ideal gas that we use is so it's going to be PV equals to nRT. PV equals to nRT. Second equation that we will use is n number of moles. N is the number of moles. Capital N is the number of particles, and N of A is the Avogadro constant. So N equals to capital N over NA. Then third one that we will use is this one. So average kinetic energy equals to 3 over 2 Boltzmann constant times temperature. Temperature has to be in Kelvin. Let's copy it down here. So EK average molecular kinetic energy is 3 over 2 kBT, which is also equals to 3 over 2 R over NAT. So R is the universal gas constant, so it's given in the data book, it's around 8.31, and Na is the Avogadro constant. So it's 3 over 2 R over Na t. Okay. Yeah. So what do we need to find? We need to find what is the gradient of the graph. So how do you find the gradient of a graph? Well, you always draw this triangle, and then you say, oh, the gradient is equals to rise over run. Our rise is on the y-axis, which is like delta v, right? Change in v, or you can just call it, uh, sorry, just call it v, right? V, because we don't have a delta v here, so to avoid confusion, we just say v. So delta v will also give you a term, will also give you the unit of v. So v, and over run, we have something with temperature. Change in temperature or just temperature, right? So V over T. So in other words, V over T or delta V over delta T will give us a gradient, right? You can say delta V over delta T and then replace the deltas with just V and T. So this is our gradient. So how do we get this capital V over capital T from this equation that we get? So we know that we have PV equals to nRT, make V over T the subject, so keep the V here. Move this capital T down there, and we have NR, and then you can move this P down there. Do we have any option that match with this thing? No, nothing match. It looks like there is no small n, so we have to get rid of this small n. So to get rid of the small n, we know we can use the second equation, and then we can sub it into here. Okay, let's do the substitution. So if you do this substitution, this will become n over na, and then r over p as it is. This is r over p. Okay. Does anyone know the option match? Let's just rewrite this thing again. So we have v over t, which is actually the gradient, is equals to n r. Maybe you can write p here and na. The order doesn't matter actually. None of them still match. Let's see how we can make use of this third equation. So if you see the third equation very carefully, by comparing the both sides of the equation, we can see that there's a 3 over 2 here, there's a 3 over 2 there also. There's a t here, there's a t here. Then it means that definitely this kb has to be equals to whatever this complicated thing is. So just by comparing the both sides of the equation, we just realize that the Boltzmann constant is also equals to r over na. Right? By comparing 3 over 2, 3 over 2, t, t, and then kb is equals to r over na. So each specific terms has to be equal to both sides. So like x equals to x, y equals to y, and then whatever equals to whatever. So r over na is actually equals to kb. So do we have r over na? Yes, we have r over na. So we can replace this r over na by kb. There we have it. So that will give us n kb over p. N kb over p. There we have our parts. Okay. This is the final answer. A particle oscillates with a simple harmonic motion system of period t. Which graph shows the variation in the time of the kinetic energy of the particle? Okay. Now this is a superharmonic motion, okay? In superharmonic motion we have, this is the ground, and maybe particle is here, and here, and here. Imagine this is the base position, so x is 0 here, so displacement is positive in this direction, and displacement is negative in that direction. Positive in this direction, negative in that direction. And here we have the amplitudes. So there are two amplitudes here, and amplitude here. So you know, at the amplitude, the body has to stop and then return. So first of all, you need to know that we need to find the kinetic energy, and kinetic energy is given by the formula half of v squared. Now, no matter the velocity is a vector quantity, it doesn't matter if velocity is positive or negative. In the end, we have to take square root of it, and square root of any positive or negative number is just positive. So this side will be positive. Positive times positive number times positive will always gives you positive. So kinetic energy is always positive. So there's no such thing as negative kinetic energy. As long as you have velocity, doesn't matter what direction, you will always have some positive kinetic energy. So ignore any option that has any negative kinetic energy. So you can see this one has a negative kinetic energy below the x-axis, so ignore A. This one is below the x-axis, this one is below the x-axis, so it has some negative kinetic energy, which is impossible, so ignore C. So we have to choose from either B or D. In both cases, we start from maximum kinetic energy. Maximum kinetic energy happens when we are at the equilibrium mean position. So here the velocity is maximum because the entire potential energy has been converted into kinetic energy. So we start from here, the body moves forward, and then it goes back here. So during the motion from here to till the amplitude, the body is decelerating as long till its velocity becomes equal to 0. At the amplitude, the body has to stop and then return. That is why the velocity has to decrease to 0. And then the body starts to gain kinetic energy and it starts to accelerate back again to maximum velocity. So during this position, this instance of time, the elastic potential energy stored in probably the spring is converted into kinetic energy. And then goes, and then the body again decelerate back to 0 here. It's because it is going toward the amplitude, and the kinetic energy is converting into elastic potential energy, and then it returns back to its equilibrium mean position, and it's accelerating back again to some maximum velocity. So you can see in this one complete time period, the velocity actually becomes 0 2 times because there are 2 amplitudes on both sides. Okay, so there are 2 amplitudes, one on the positive side, the other one on the negative side, and at the amplitude the velocities has to be equal to 0 because the body has to stop and then it has to change its direction. So there are 2 zeros there, 0 velocity means 0 kinetic energy, so that's why we have to choose D part, not A part, because this A is for half the amplitude, half the time period. But for one complete time period, the body has to stop 2 times, and also, yeah, it has to stop 2 times. 2 amplitudes. A light ray is incident on an air diamond boundary. The refractive index of diamond is greater than 1. Which diagram shows the correct path of the light ray? So, show you what is the formula for refractive index. So here we have that the ratios of the refractive index is equal to ratios of the sine of angle of in medium 2 divided by sine in angle in medium 1 divided by ratios of the 2 velocities. So in this time our refractive index is bigger than 1. So always remember, when the refractive index is bigger than 1, it means, no wait, our situation is something like that. So refractive index here is equals to the refractive index in diamond versus refractive index in air. And this is also equals to velocities in air over velocity in diamond. It means if the refractive index is bigger than 1, it means there is a bigger velocity in air than the diamond. So always remember, when the refractive index between the 2 boundary medium, between the boundaries of the 2 medium is bigger than 1, there's a phenomenon called total internal reflection that always takes place. So total internal reflection says that when the refractive index is bigger than 1, the incident wave, so this is the incident ray and this is the angle of incident, will no longer refract into the different medium, but it will reflect back into the same medium with the same angle of reflection. So the angle of incident is equal to angle of reflection. Total internal reflection will take place if the refractive index is bigger than 1. So you can see there's a refraction going on here because the wave is moving, is passing from one medium to another medium, because air and diamond, they have different densities, hence they have different medium. There's a refraction happening here also. They're bending away from the normal. There's nothing going on here. I mean, there should have been some refraction, bending away toward the normal. here there is a total internal reflection happening. For example, if the ray hit back to a different surface, and if the refractive index is still bigger than 1, then there will be a second total internal reflection happening. So it will keep on reflecting within the body. And this is a phenomenon that is also used in fiber optic cables to transmit information in form of light instead of current. So in fiber optic cables, the refractive index is maintained at bigger than 1 to make sure that the light ray doesn't refract into different medium or outside the fiber cable, but the light ray stays within the fiber cable so that they can be totally internally reflected and transmitted from the through the transmission line to the receiver, from the source to the receiver. Okay, so it has to be the point source of a light with an amplitude A0 give rise to a particular light intensity when viewed at the distance from the source. When the amplitude is increased and the viewing distance is doubled, the light intensity is doubled. What is the new amplitude of the source? Okay. So here we have to actually use two equations from the wave, and these are the twos. So the amplitude, the intensity is directly proportional to square root of amplitude, and intensity varies inversely proportional to square root of distance away from the source. So intensity of light is directly proportional to square root of amplitude, and intensity of light is inversely proportional to square root of distance from the source, right? If you combine these two equations, this thing can also be written as 1 over x squared, simple indices, because we don't like this negative 2. You can always bring it down. Okay? So if you combine these two equations, we can also rewrite this one in a single form. We can say, oh, intensity is directly proportional to square root of amplitude, but inversely proportional to square root of distance from the source. So this is also true. Okay. All right. So if this is true, what we can do, we can just ignore the proportionality sign and we can just replace it with some constant k. We always replace proportionality with some constant k. Then we have a squared over x squared. Since what is a new amplitude? Since we are trying to find the new amplitude, make the amplitude the subject of the equation. So a squared equals to x squared goes to the other side. So we have amplitude times x squared over k. Now to get rid of this square, we have to take square root on both sides. So amplitude will be equals to pi x squared over k. So this is the equation that we will be using. So amplitude in terms of intensity, displacement, and some constant. So the situation here is we have a light source that is producing some light, and it has an amplitude of A0. Gives rise to a particular wave, particular light intensity when viewed at the distance from the source. Okay, probably the distance from the source is maybe x. Call it maybe x0, and O for initial. And here we have some intensity naught. Okay, yeah. When the amplitude is increased now, we have the same light source but twice the amplitude. And the viewing distance is double, and this distance is also double, so it's 2x0 this time. What will be the new intensity? This is the situation. Yeah, so the distance is double. The light intensity is also doubled. Oh. When the amplitude is increased, so actually it looks like we're increasing the amplitude, so we have some new amplitude that we don't know. When the amplitude is increased and the viewing distance is doubled, the light intensity is doubled. So this light intensity we already know now. This light intensity is actually going to be 2 times I0. Initially, if the light intensity is I0, the new light intensity will be 2 times I0. And what will be the new amplitude to make sure that twice the distance away from the source, the new intensity will be doubled? Okay, now we already have our equation, so we just need to do like this. So we will say, okay, the new amplitude equals to So amplitude is equals to intensity. So our intensity is 2 times the original intensity. It is twice the original intensity times, so there's a displacement here, we have to take the square. How much is our new displacement? So new displacement is twice the original displacement, just call it x, no need to write x naught, divided by k. K is a constant which still stays the same. Okay? Yeah, is any problem till here? I'm sure there's no problem till here. First of all, we combine these two equations. So intensity depends on two things. It depends on the amplitude and the displacement from the source, the distance from the source. Combine them together, form a single equation, replace proportionality with a constant k, and then try to make amplitude the subject. Why are we making amplitude the subject? Because that is what we need to find. What is a new amplitude? So the situation is that initially you have an amplitude of a naught, at a distance of x naught, you get intensity of I naught. The second time, what will be the new amplitude, so that if you place the receiver at twice the distance away, you will receive twice the intensity. So we just need to replace I and x by the new terms, and then try to write this A in terms of the original amplitude. So as you can see, 2 squared is 4, 4 times 2 is 8, so we will have 8 here, then we will have I x squared over k squared. Now, we have to take the square root of 8 common, and we have to take the square root of 8 out, so we can do something like this. Okay, this is correct, using indices. Now realize what is, call it new amplitude, call it A2. The new amplitude is, what is this? Square root I x squared over k, square root I x squared over k. This is actually equals to original amplitude. So there we have our result. So this is equal to the square root of 8 times A. Okay. So is there any option that says that the new amplitude is square root of 8 times A? There is none. But what we can do is we can further manipulate the square root of 8. You know, square root of 8 can be written as square root of 8 is 4 times 2, and then there's A, and square root of 4 times 2 can be written as square root of 4 times square root of 2, and then times A, and then square root of 4 is just 2, and square root of 4 is 2, and then the square root of 2, and then there's A. So this is equivalent. 2 square root of 2 is equivalent to square root of 8. So our new amplitude is 2 times square root of 2 times A. So it has to be B. Okay. Yeah, maybe you can call this one as initial amplitude, call it A naught. So this is A naught, A naught, A naught, A naught, A naught, and this is A naught. Okay, A2 is a new amplitude, so we have to write new amplitude in terms of original amplitude by changing the intensity and the displacement from the source. This diagram shows the shape of the wave front. So wave fronts are the waves that we observe as we look from the top. So the distance between the two wave front. Actually, this wave front can represent either two consecutive crusts or trough. So this is the crust and this is the trough. The wavelength is lambda. As a result of diffraction, so diffraction happens when the wave passes through a bend or a narrow gap. So when it passes through such an obstacle, there's always bending of the wave. So the wave diffracts, spreads around that region of space of a plane wave by an object. So there's an incoming wave. Okay, and let's look at the C pi. C pi is totally impossible because this obstacle is going to block. It's going to block this part of the wave, right? This part. I mean, this part of the wave should have been blocked. Alright, this part of the wave should have been blocked, but it looks like, what is this part of the wave still doing it? So C is wrong. And also remember, for example, a simple case will be like, if you have a wave front here and then it passes through a slit, all these waves, they bend away from this. It's just, they actually bend at the corner. So the bending actually starts at the corner. For instance, if you have a wall here and there's a person standing here and the person is speaking, so the wave starts to bend at the corner. So there will be very little changes happening here, but significant changes happening at the corner. So the wave will be bending at the corner. So yeah. So you can see here, no, this one, I mean, this car should not have been there at all because it should have been blocked by this obstacle. So this is totally wrong. So okay, and also about the bending. So where you have a corner, the wave actually starts to spread out at the corner. So for example, if you have a corner here and then there's a wave coming in, what will you expect? The wave will actually be like this. Start bending at the corner. Okay, so it looks like A part is correct because you can see the wave is actually bending and spreading away from the corner. So this corner, and this part has been blocked. It's blocked here, this is blocked here, but here the wave is being converging inside, but it doesn't converge inside. It actually spread out. So that's the whole point of having diffraction. So diffraction actually causes a wave to spread out of the medium, so spread to a wider, bigger space. Okay, diffraction. So number 16. A negative 5 microcoulomb charge and a positive 10 microcoulomb charge are a fixed distance apart. What can the electric field, where can the electric field be zero? None. Electric field strength is defined as the amount of electrostatic force acting on per unit positive test charge. Okay. So the electric field strength is a vector quantity which is given by electrostatic force acting on per unit positive test charge. So whenever you want to measure electric field strength at any point, you always introduce a small unit positive test charge. Now, for instance, if this is the body, the charged body, whose electric field we are trying to measure, so you can see this is already the output electric field. And if you want to measure the electric field strength at, for example, this point, then you always introduce a small unit positive test charge and then measure the electrostatic force acting on it. So electric field strength is also vector quantity, so it is direction dependent. You can cancel it out. You can find the net electrostatic field strength. Yeah. So in order to measure, so first of all, let's figure out what is happening at position 1. So to find the electric field strength at position 1, you always introduce a small unit positive test charge. Okay, and then measure what are the electric field strength acting on it. So positive repel. So you can see this is the electric field strength acting on this small test charge due to this positive coulomb. And then is there any other charge here? Yes, there's a negative 5 coulomb. So positive, negative attract each other. So this is attraction. So it's going to be electric field strength due to this negative charge. So these are two vector quantity. Now, okay, so there's a positive. So there's electric field strength acting on this test charge due to positive 5 coulomb and also due to negative 5 coulomb in the opposite direction. They're pulling this in different directions. This one is repelling. This one is attracting. But electric field strength is a vector quantity. Now, what do you think will be the net resultant electric field strength? Now, what is the reason why did I draw this electric field strength as smaller? The length of this arrow is equivalent to the strength of the electric field. So the length of the arrow is actually equivalent to the magnitude of the electric field strength. Well, the electric field strength is directly proportional to electrostatic force, and the electrostatic force due to this one will be smaller because negative 5 coulomb is a smaller charge in magnitude and is also further away. So this one being a smaller charge and further away from the test charge will lead to a smaller electric field strength. That is why I drew a smaller length arrow. Okay, and well, this one will be bigger in magnitude because this positive field strength acting on this test charge is due to this plus 10 microcoulomb. It's a bigger charge and it's even much closer to this test charge, hence the repulsive force will be bigger, right? So just as a reminder, the electrostatic force is is directly proportional to the product of the two charges and inversely proportional to square of the distance between them. So as the distance increases, the force decreases, and as the charge increases, the force increases. Okay. So there's no way these two forces can cancel it out. These two electric field strength can cancel it out each other. Hence, it looks like there will be some net force in that direction, and it won't be zero anymore. Electric field strength net. So it can never be zero because this one is always smaller than this one because it's smaller charge and it's further away. So this position 1 is gone. So ignore any option that says position 1. Alright, let's just test position 3. So in order to measure the net electric field strength at position 3, always introduce a small unit positive test charge. Okay, and then measure what are the electric field strength acting on it from different charges. So let's see what is the behavior to this negative charge. So negative and positive attract each other. So electric field strength on test charge due to this negative Coulomb. Okay, and then is there any other electric field strength acting on this test charge? Yes, there's an influence of this plus 10 microcoulomb. So plus positive repelled. So there will be a repulsive force in the opposite direction. So this is the electric field strength due to this positive Coulomb. Well, even though this one is a bigger charge, so apart from being a bigger charge in magnitude, it's also further away from this test charge. So there's a possibility that the electric field strength, this one, can be equals to this one. Yeah, because even though it's a bigger charge, but it's still further away. So though this part has increased, but this part also increases probably at the same proportion. So there's a very high chance that the negative electric field strength is equivalent to positive electric field strength, and they will just cancel it out each other because they're vector quantity. So the position 3 has a maximum chance for the electric field strength, the net electric field strength to be zero, because this negative charge causes this electric field strength in the positive direction, and this positive 10 microcoulomb charge causes this test charge to repel in the other direction. And even though it's a bigger charge, but still it's further away from the electric field strength. So there's a high chance that the magnitude of the electric field strength due to this positive charge can become equal to negative charge, and they can cancel it out each other because they are occurring in the opposite direction, and that can give us a net electric field strength of 0. So position 3 is the most likely position where the net electric field strength or electric field could be 0. So part C is the answer.